Hi everyone, my name is Andy. I'm with the Speech Lab from National Taiwan University. I'm here to present our work as the first author. The title of our paper is Mockingjay, Unsupervised Speech Representation Learning with Deep Bidirectional Transformer Encoders. So, let us begin. BERT is a very well-performing language representation model, which is unsupervised trained from large amount of unlabeled text. When input with text tokens, the model outputs representations. When used with downstream NLP models, such as QA model, summarization model, through feature extraction or fine-tune, BERT achieved many state-of-the-art results. Inspired by BERT in NLP, we aim to build a speech version of BERT, which will be unsupervised trained on large amount of unlabeled speech. Instead of taking discrete tokens as input, the speech BERT will take acoustic frames, and a sequence of representation will be generated for each utterance. Once trained, speech representations can be extracted or fine-tuned with downstream speech models. In this talk, I will introduce how we use speech BERT to learn speech representations. First of all, I would like to go through some of the recent unsupervised speech representation learning approaches. In 2018, DeepMind introduced the Contrastive Predictive Coding Approach, CPC. A 5-layer CNN with a sequence model of GRU is used to encode past context, while the model predicts the future to solve the contrastive binary classification task. In 2019, MIT introduced the Autoregressive Predictive Coding, APC. Largely inspired by language models LM for text, the APC model can be seen as a speech version of text LM. Both the CPC paper and APC paper evaluated with downstream phone and speaker classification tasks. The APC approach devotes its effort in comparing with CPC and claims to outperform CPC. Note that the CPC and APC approach shares a common heuristic. That is, they both encode past information and predicts information about future frames. In contrast, the proposed Mockingjay predicts the current frame by jointly conditioning on both past and future contexts. During training, masked frames are given and the model learns to reconstruct and predict the original frames. Hence, we gave the name Mockingjay, following the bird that mimics sound. At inference time, sequence of frames are given and the model generates the desired representations. In this work, following CPC and APC, we evaluated with phone classification and speaker verification as well. In addition, we also set up a third downstream task, sentiment classification on spoken content. Now, let's go into details about the proposed pre-training task, which we use to pre-train our transformer encoders. We will illustrate the pipeline from input to output. First, we have some real frames at the input. These frames are phoneme-level spectrograms. Next, we have a masking probabilistic policy that will mask frames to 0 at random. These masked frames will then be the input to our model during training. So, after we mask those frames, we feed them to our model. We use multiple layers of transformer encoders with multi-head self-attention to achieve bidirectional encoding. The output of the last encoder layer is thus the representation we want. Note that we only ask the model to predict the masked frames and not all of the frames. We outline them in red. These representations are fed through a prediction head, and the model then tries to predict the missing frames with a feed-forward network. For example, the frame C is masked to 0, so the model predicts and reconstructs frame C at the output. Hence, the model tries to reconstruct real frames from corrupted input, where we use L1 loss to minimize reconstruction error. The idea is that if the model can predict the missing frames from neighboring frames, then it should provide a good bidirectional understanding of the past and future content, as the representation considers the whole utterance. Here I will introduce how we mask frames at random. During training, we use a probabilistic policy to generate masked frames dynamically. We illustrate the policy and the process in this page. In the first step, we randomly select 15% of the input frames for masking. In the second step, for all the 15% selected frames, we roll the dice again. For 80% of the time, we mask all the frames to 0. So, for example, frames B and D will be set to 0. For 10% of the time, we replace the selected frames with random frames. For example, frames B and D will be replaced with a random frame G and Y within the same utterance. For the other 10% of the time, we leave them untouched, so the input frames is identical with the original ground truth frames. Note that only one case will happen at a time. Either we mask all 15%, replace all 15%, or we do nothing. To sum up the proposed pre-training task, we will show some illustrations. Here we show how the input features looks like. We use 80-dimensional Mel spectrogram with its first derivative. The mask frames are highlighted in yellow. So the model takes mask frames as input and generates Mockingjay representations. Then the model predicts and reconstructs the original frames. L1 loss is used to compute the reconstruction error. Note that the predicted frames and real frames looks almost identical. They are real samples, while the hidden representation looks nothing like them. Now, I would like to address some of the main differences between BERT, a NLP model that operates on discrete text, and our model, Mockingjay, that operates on acoustic features. As we all know, acoustic features can be very long in sequence length and locally smooth. Hence, we need to try to shorten the input sequence and mask over a longer span. The solution to the above two problems are downsampling and consecutive masking, which we will illustrate below. At the bottom left, we first show how we apply downsampling on input features to adapt our model to long sequences. To reduce the length of frames by a factor of r, we use the reshape technique by stacking r consecutive frames into one step. We illustrate the case where r is equal to 3. At the bottom right, we show how we use consecutive masking, where we mask consecutive frames c to 0. By masking a longer span, the model is required to infer on global structure rather than local information. We illustrate the case where c is equal to 3 and how consecutive masking works with downsampling. I would like to go over some details about the model. At the left side, we illustrate a conventional transformer encoder block, which consists of multi-head attention, feed-forward network, and residual connections. Here we also list some of the parameters. The hidden dimension is 768 with feed-forward dimension of 3072. We use 12 attention heads and pre-train for 500,000 steps on the LibreSpeech 360-hour subset. When we fine-tune the Mockingjay model with downstream models, we fine-tune for 50,000 steps, which is approximately 2 epochs of training data. We train two models, the base model with 3 layers and the large model with 12 layers. There are a total of 3 ways to incorporate the pre-trained Mockingjay model with downstream tasks. In this page, we illustrate the first way, which is to extract features from the trained model and use them as speech representations. At the right-hand side, we pre-train the Mockingjay model like mentioned in previous slides. Next, we freeze the pre-trained model and use it for feature extraction. Here we illustrate an example downstream model. For example, it can be a phoneme classifier or a speaker classifier, which we will train with little pair data. There is a green box here, which illustrates that the supervised loss is applied on a classifier only, and no gradient will flow through the frozen Mockingjay model. The second case, we extract features from all layers. In other words, we expose the deep internals of Mockingjay to downstream models. Same as the previous case, we have a frozen Mockingjay model here, but instead of using the last layer's hidden state, we use the hidden states of all layers. Here we illustrate how to use a mixture of representations from all layers. All the hidden representations from all layers are integrated into a new representation through weighted sum. Note that all the weights are learned from data, and we denote this approach as WS in later experiments. The third case, where we fine-tune the Mockingjay model with downstream classifiers. Same as the previous two cases, we have a pre-trained Mockingjay model at the right-hand side. In the fine-tuning case, the downstream model consists of the Mockingjay following a classifier, where we initialize the Mockingjay model with the pre-trained weights from the right. The loss is applied on both the classifier and the Mockingjay model. The Mockingjay model is no longer frozen and updates with the classifier. When we fine-tune our models with little data, we fine-tune for 2 epochs only, and we denote this kind of setting as FT2 in later experiments. We present results of 3 downstream tasks, including phoneme classification, speaker recognition, and sentiment classification on spoken content. First, we will talk about the phoneme classification task. The phone classifier performs frame-wise classification with a feed-forward network, and is trained on the LibreSpeech 360-hour subset tested on the test-clean subset. There are 73 possible phone classes, which we obtain through force alignment. The other 2 tasks use a RNN classifier, which takes an utterance as input and output a single classification result. We illustrate this at the bottom of the page. The speaker recognition classifier is trained on the LibreSpeech 100-hour subset, where train and test split is performed randomly with a 9:1 ratio. There are a total of 63 possible speakers. The sentiment classification classifier is trained on the MOSEI dataset. However, the Mockingjay features are pre-trained from LibreSpeech. We use this third task to evaluate transferability across different datasets. In this table, we list results of the 3 downstream tasks. We see that results are consistent over all the 3 tasks, where the base model outperforms the baseline male features, while the large model outperforms the base model. Here we list the results where we extract features from all layers and integrate them with a learned weighted sum, denoted as large WS. First, we see that integrating hidden representations gives a performance boost over all tasks. Next, we see that fine-tuning also gives a performance boost, in particular in the phone classification case. In the last row, we also report results of the reproduced APC approach. The base FT2 model achieved the highest score on the phone classification task and speaker recognition task, outperforming all features, whereas the large WS model achieved the highest score on the sentiment classification task, outperforming baseline and APC features. To demonstrate how pre-training on speech can improve supervised training in low-resource scenarios, we train the classifier with reduced amount of labeled data. The performance variation of different models are plotted in the figure, where we measure over various intervals of constrained training data to observe performance drop. We first show male feature performance in the blue curve. Next, we see how the base model increases accuracy over male features across various amount of transcribed data. Here we have the large model outperforming the base model in some cases, while the large model also outperforms male features across various amount of transcribed data. By using the weighted sum approach, the large WS model boosts performance over the large model, which results in an average 5.75% performance boost. We discovered another interesting fact. Large WS with 52.8% accuracy even outperformed male features with 49.1% accuracy that uses all 100% of labeled data. We highlight these 2 data points in red and blue boxes, respectively. By fine-tuning the base model, the base FT2 model outperforms all others over all amounts of labeled data. We plotted an additional data point where we fine-tune for 500,000 steps, called base FT500, which is highlighted in a purple box. We use this to show that fine-tuning for 2 epochs is enough to reveal our method's potential, as there is only a small gap of 3.9% between base FT2 and base FT500. Note that with only 0.1% of labels available, base FT2 outperformed male features that uses all 100% of labeled data. We highlight these 2 data points in purple and blue boxes. And finally, the APC approach performs well on the full resource, but fails to generalize for limited amount of labeled data. We conclude that Mockingjay pre-training substantially improved performance on supervised tasks that requires human annotations.